Hi there, this video is going to walk through some ideas about atomic spectroscopy and our Bohr model. The first thing we'll talk about is something called an emission spectrum. Okay, so an emission spectrum is generated when you have an element that gets vaporized. So in our picture here, this little glass tube here would be full of a gas phase element. So maybe hydrogen or mercury or helium or neon. Some gas phase element, okay? If we excite that gas inside of that tube, it's going to give off some light, okay? You're going to see it start to glow and give off light, okay? So we can excite it by heating it. We could put that element in a flame, or we could apply some voltage, some electricity to it to excite it. So what we're doing there is essentially exciting electrons that are in that gas. And when those electrons get excited, they jump up to high energy levels, and then at some point they relax back down, and when they relax back down, they give off a light. And we can detect that light. Okay, if we shine it through a prism, we'll actually see the different components of in this case we're showing the visible light region. Okay, we'll be able to detect the specific wavelengths of light that each element gives off. Okay, now each element has a very specific signature of wavelengths that it will emit. Okay, so it's kind of like a little fingerprint for our elements. Okay, so here is one example for our simplest element, hydrogen. Okay, these are the visible lines that you'll see if you were to look at the light emitted from an excited sample of hydrogen with a prism. You can use even a CD. If you hold a CD up to that light, you'll see all of these lines, these colored lines show up. Okay, so these are the lines that you'll see for hydrogen. You'll get to work with this in lab, okay, but you see we get a red line, a green line, a blue line, and a couple of lines into the purple and UV regions. Oh, and I just noticed a typo on here that I'll fix right now. So these are actually called bright line spectra. We'll talk about dark line spectra on the next slide. Okay, so let's talk about a kind of a same but different process from what we just talked about. So this would be the dark line spectrum for hydrogen. Okay, we call this also an absorption spectrum. So here we're just kind of looking at the opposite process from what we just looked at. So in this case, we have a source of light, a source of white light, so it's shining all of the wavelengths of light onto your sample. Okay, so this would be, in this example, a sample of hydrogen. Okay, so as the light goes through that sample of hydrogen, the hydrogen's going to absorb very specific frequencies of light or specific wavelengths of that light that's coming in. And again, we can use a prism to help us to see the different wavelengths of light that are absorbed by that sample of hydrogen. And in this case, we see that instead of seeing bright lines on our detector, we see a bunch of dark lines on the rainbow. Okay, so these black lines will actually match up with the bright lines that we saw in our bright line spectrum. All right, so they're going to be located at exactly the same wavelengths as we had over on this spectrum. Now, this phenomenon was really strange to physicists and chemists back in the early days. Okay, they didn't have a good way of explaining why they were observing these discrete lines in the spectrum when they would look at these different samples with the prisms. Okay, so it took a long time before someone was able to explain why you only see these certain very specific wavelengths that get absorbed or emitted by these different gases. The hero of our story is actually a scientist named Planck, Max Planck. who devised the idea of quantization of energy. And this was a really revolutionary addition to the science back when this first started. So we're not too long ago now. We're talking back in the early 1900s is when these ideas started to come into play, these ideas of quantization of energy. Okay, so what Planck proposed was that light emitted from atoms and molecules must be quantized. Okay, so that means that only a discrete or a very specific number of particles of light, which we call photons, it's our new word of the day, only discrete numbers of particles of light can be emitted by our atoms and molecules. Right, and mathematically, we can say that by saying that the energy of our atoms or molecules can be represented by a constant. We call this Planck's constant. H is 6.626 times 10 to the minus 34 joules second, so a very tiny number, times the frequency of our light. Okay, so it's only very specific values of, if we look at our values over here, only very specific values of energy are allowed for our atoms and molecules. Okay, and we can also put that in terms of wavelength. Okay, so we have an energy in terms of frequency. You'll often see this h nu be used to represent light, the idea of light or photons in a system. Okay, we can also represent it in terms of wavelength or lambda. Okay, so lambda would be our wavelength of a atom or molecule. Okay, and then nu is the frequency. Okay, so however you want to think about it, either one of those will. All right, so what Planck is saying here is that your electrons in your atoms and molecules can't occupy any value of energy like classical physicists originally thought. So the original thinking was that you can occupy any energy between 0 and infinity. There was no limit there. Okay, but that didn't explain what they saw in their atomic spectroscopy observations. Okay, so assuming that electrons can occupy any energy does not explain what the scientists were seeing in their experiments. It didn't explain these discrete lines. Okay. What did help to explain it was, again, Planck's introduction of this idea that your electrons can only take on very specific values. Okay, so we can write that equation form again like this, and then we can also represent it pictorially. Okay, so here's what we call an energy level diagram. Okay, so when you see these diagrams with energy on your y-axis and a bunch of horizontal lines, that is referred to as an energy level diagram. Okay, so here each horizontal line essentially represents an allowed energy of this particular atom or molecule. Okay, so in this case, these allowed energies are equally spaced. Sometimes they're not. Sometimes they'll get closer together, like you'll see for the hydrogen atom. Sometimes they get further apart as you go higher in energy. Okay, this is just one sample example. Okay, so Planck's idea of quantization is really why we draw these energy level diagrams that you might have seen before. Okay, so looking back at our absorption and emission spectra here, our dark line and our bright line spectra, we can illustrate what's going on in terms of Planck's idea of quantized energy levels. So what's happening is we have one energy level. We'll say it's, we'll call that energy level 1. We'll call this energy level 2. Okay, so for a given molecule, in this case we have a picture here of the sodium emission and absorption spectra. What's happening that gives rise to those lines is for absorption, you're absorbing energy. So we're going to draw an arrow that goes in the up direction. Okay, so this is basically we're shining light onto our sample, and that electron absorbs energy and jumps up into that higher energy level. Okay, so H nu, that's our light or a photon, however you want to think about it. Okay, so this is the absorption process. Okay, so up arrow is absorption. All right, so once that electron gets excited up into that higher energy level, then it, at some point, can't stay there unless you put a constant stream of energy in there. So at some point, it's going to drop back down to the original level. Okay, so in that point, when it drops back down, it has to release that energy that we put into it. Okay, so we put this H nu of energy in, bumped up here, and then once that electron decides it's time to relax back down, it has to get rid of that same amount of energy. Okay, so we can draw that with another squiggly arrow that says we're giving off some light. Okay, and then this is our emission process. Okay, so the down arrow is what would be our emission process. So this is our bright line spectrum that results from that. And then this would be our dark line. So we're absorbing that light. Okay. All right, so now that we have this idea of quantization of energy from our buddy Planck, the stage was set for the other scientists of the day to start to be able to explain why these observations were occurring, why they were seeing these experimental observations. Okay, so now we have another quantum chemistry heavy hitter coming into the game. So you've probably all heard of the Bohr model. So Bohr borrowed some ideas from Planck, that quantization idea, to try to see if he could explain the hydrogen emission spectrum. Okay, so Bohr used a few assumptions, okay, again, based off of that quantization idea from Planck, and his assumptions were that the electron in hydrogen can only occupy specific energy levels. Okay, so that's that quantization idea that he borrowed from Planck. Right, and then he also said that the electron can move from one energy level to another. Okay, so that's what we just drew a minute ago. So the electron can get excited. Okay, it can jump up to an energy level that's higher than it was, and then it can relax back down to a lower energy level. Okay, the caveat there is that you have to put in exactly enough energy to be able to reach that higher energy level. Okay, so you can't put in enough energy to excite it halfway between your energy levels. Okay, so that's kind of like it would be like trying to jump up onto a step and not quite making it all the way. Okay, you're not just going to hover in the air in that case, right? What's going to happen? You're gonna jump up, not quite make it, and then you fall back down. Okay, so in order to get up to these higher energy levels, you have to put in enough energy to match those energy levels. So we need to be able to jump to here, or we could jump all the way up to here if we put in enough energy. Okay, but you have to get up to those defined energy levels for your particular atom. Okay, so we say that as long as we have the delta E for that particular transition, as long as we put in delta E of energy, then we can excite our electron up to that transition. Okay, so we can go, if we put in enough energy to get from n equals 1 to n equals 3, okay, then our electron can get up there. All right, so the next idea that Bohr proposed was that energy levels are designated with the letter N. That's our principal quantum number. We'll see that down the road when we talk about our quantum numbers. Okay, it's just one way that we label the energy of our atom. Okay, so N only takes on integer values. Okay, so 1, 2, 3, 4, 5. okay? And our lowest energy level is n equals 1, okay? So this is what we call our ground state. That's our natural, relaxed, lowest energy state, okay? So Bohr postulated that emission spectra will occur, those bright line spectra, okay, that we saw before. He said that those emission spectra will occur when electrons move from a higher energy level to a lower energy level. Okay, so we're going from a higher energy level down to a lower energy level, and that's our emission process that we talked about. Okay, so these are the assumptions that Bohr made, again, borrowing from Planck's idea of quantization. Okay, he devised all of these assumptions as a way to explain the spectra that we see for the hydrogen atom. So I'll go back here. Using those assumptions, Bohr was able to actually predict where all of these lines would show up. Okay. All right, so the equation that Bohr is able to derive from all of these assumptions is shown right here. Okay, so this delta E essentially represents the energy of what we call the transition. So remember, when we say transition, that's just referencing a jump between two different energy levels. Okay, so any transition, so from n equals 3 to n equals 1, from n equals 7 to n equals 2, okay, those are all what we call transitions, and there's going to be a delta E associated with any of those transitions. So that's what we're talking about when we say delta E. Okay, so that energy transition Bohr figured out with his assumptions was given by this equation here, where RH is what we call Rydberg constant. Okay, so this is, if you see this word flying around, that's your Rydberg constant. It's actually one of the most well-known constants, physical constants that we have. Okay, it has a value of 2.18 times 10 to the minus 18 joules. Okay, and then the other part of this equation just shows you the transition that's happening between your energy levels. Okay, so here your initial energy state, n sub I, you're going to square that. Okay, and then this represents your final energy state, and you square that as well. Okay, so as long as you know what energy levels you're transitioning between, you can calculate the energy associated with that transition. Okay, and then once you know the energy, you can calculate your frequency and your wavelength associated with that transition as well. Okay, so this is the magic equation that Bohr developed that explains the locations of all of those lines that we see in our hydrogen atomic spectrum. All right, let's do some practice here. So let's practice using Bohr's equation. Okay, so Bohr came up with this nice equation that allows us to predict the energy transition. So when you look at this picture of the hydrogen atom energy levels, all of these arrows, these emission arrows going down, okay, basically represent a delta E. Okay, so the longer the arrow, the larger the change in energy. Okay, so that's what we're looking at here. Okay, and then these, remember these Balmer lines. Okay, these are our visible lines. Okay, so you'll work with that in lab a little bit more, but those ones are the ones that we can see with our eyes. All of these other ones are kind of in other areas of the electromagnetic spectrum that you need some other kinds of instruments in order to be able to detect. Okay, so let's practice calculating a wavelength. Let's predict a wavelength. So let's predict the wavelength for the transition from n equals 5 to n equals 2. Okay, so where's n equals 5? So we're going to go here. It's this line, essentially, in our Balmer series that we're going to calculate. Okay, so we've got n equals 5 to n equals 2. All right, so where do we want to begin? So we have information about both of our ends. Okay, so we have an N initial and an N final. We have the RH, right? We're given that Rydberg constant right here. So we have everything we need to be able to calculate a delta E. All right, so why don't you take a minute, pause the video, see if you can set up that calculation and calculate the delta E associated with the change in energy state for our electron from N equals 5 to N equals 2. And then we'll come back here in a minute when you're finished. Okay, so here's what I ended up with. Take a second to compare it with what you predicted for your calculation. Okay, so here we have our delta E equals our Rydberg constant, so 2.18 times 10 to the minus 18 joules, times our 1 over N initial, so we started at N equals 5, okay, minus 1 over our N final squared, so we ended at N equals 2. Okay, so we've got 5 squared and 2 squared in our denominators. Okay, so this is an emission process, right? We're going from a higher energy to a lower energy. So remember, that's an emission process. Okay, so we're going to give off some light, okay? And the energy of that light that we're giving off, we can calculate with that equation, and hopefully you come up with negative 4.58 times 10 to the minus 19 joules. Okay, now you might be asking yourself, gee, it really doesn't make a whole lot of sense to have a negative energy necessarily, right? Because we're going to be using this to calculate a wavelength, which needs to be positive. Okay, so one thing that we can keep in mind here, so I have this little note down here, the value that you get out from that calculation, if it is negative, all that's telling you is that you have an emission process. It's just telling you that you're going from a higher energy to a lower energy level, okay? If we were to swap that and do the absorption process, so if we had the 2 squared here and the 5 squared over here, so if we're going up in energy from N equals 2 to N equals 5, okay, that sign's going to flip. Okay, we would have ended up with a positive value for delta E. So if you get a positive value when you do this calculation, that just tells you that you're doing an absorption process. Okay, so we did an emission process, so it makes sense that we're going to get a negative value out of there. Okay, all you have to do moving forward is to take the absolute value of your energy. So a lot of times you'll see the requested information that you want, whether it's in a lab or on another assignment, is we're looking for the absolute value of that energy. So we can just put our absolute value signs there, take the absolute value, and that makes it positive. Okay, but just doing that equation as written, the signs will just kind of tell you if you're doing emission or absorption. Okay. All right, so we're not quite done with our problem, right? So the question's actually asking us for the wavelength in nanometers, not the energy. So we have one more step to do. So if you recall, go back in our slides, we still have this handy equation that we can use. Okay, so we have our energy, essentially we have our delta E, okay? So we can use this relationship here to get our wavelength. Okay, so let's do that last part of our calculation. Okay, so we want delta E equals HC over lambda because we want wavelength, okay, not frequency in this case. So let's rearrange this so that we're solving for the quantity that we want. Let's rearrange this to solve for lambda. Okay, so take a second and see if you can rearrange that expression to solve for lambda. Okay, so let's see, hopefully you end up with what I do. Okay, so, and we can again remind ourselves that we want to use the absolute value of delta E here. Okay, a lot of times we just won't put that in, but know that you want to use the positive value for your delta E in all of these equations. Okay, so we have an expression to solve here. So we have couple of constants up top. So we've got Planck's constant we know, we have c, which is the speed of light that we already know, and we've already just calculated our delta E. So that's our 4.58 times 10 to the minus 19 joules. So we're in business. Okay, so now we can calculate our wavelength. So lambda equals, plug in your values. So we have Planck's constant times our speed of light, 3 times 10 to the 8 meters per second, over our delta E, which we just calculated, which is 4.58, times 10 to the minus 19 joules. Okay, so punch that into your calculator and see where we end up. So while you're doing that, I'm going to take a look at our units and see how things are canceling. So the joules are going to cancel, the seconds are going to cancel with the per second of the speed of light, and we're left with meters. Okay, so the number that you get out here is going to be in units of meters. Okay, so hopefully you've done that and you end up with 4.34 times 10 to the minus 7 meters. Okay, but our question, go back and double check, is asking for nanometers. So we have one more step. Okay, so we want to convert meters to nanometers. Again, take a second, pause the video and take a second to do that conversion. Okay, so in that case, we are going to, running out of room, but remember your dimensional analysis. So there is 10 to the minus 9 meters in a nanometer, or you could say 10 to the 10 nanometers in a meter. Okay, punch that in your calculator and you will, or maybe you can do the exponents in your head. Okay, but either way, hopefully you end up with 434 nanometers. Okay, so if you go back and look at your electromagnetic spectrum, you should see that 434 nanometers falls in the visible part of our spectrum. Okay, it's actually going to be towards the blue. All right, so there is our answer. Okay, 434 nanometers. Let's go look at our hydrogen spectrum and see if there's a line at 434 nanometers. Double check ourselves. Okay. Oh, hey, would you look at that? So we have a beautiful matching line for what we just calculated. There's our 434 nanometer blue line in our hydrogen emission spectrum. So that is our n equals 5 to n equals 2 transition. Okay, so hopefully this helps you feel comfortable with working with those equations related to our Bohr model and calculating the energy transitions for these for electrons going to different energy levels. Okay, so keep practicing with that, and we will keep having some fun with this in lab. All right, thanks guys.